Bismillah ar-Rahman ar-Rahim. Hello, my friends. This is Dr. Mohamed Nezami again coming to you from Jerash, Jordan. Welcome to my lectures on YouTube posted right now. This is a new series that I'm starting. Just to remind you, for some of those that may watch this for the first time, this is my YouTube channel. You can get it at this address here. And what I have a whole bunch of videos on the theory and practice of radio frequency and microwave circuits and system designs. Okay. Now, the also among these videos, they're also organized in a playlist, and you can see the playlist. This is where they are. And you can see any particular thing that you're interested in, you can go in and watch it all. And now so today I'm gonna start. This is what I'm presenting here. Really is a proposed new way of designing a Ka band LNB low noise block down converter for SATCOM applications. Now, what I do is I work as a freelance consultant. I design remotely. I work remotely with clients in the United States, Europe, India, Middle East, on designing inexpensively designing and developing RF and microwave module systems and whatever. I basically take your concept or specifications and requirements and turn them into system architecture. I build it for you. I model it, proof concept it, and then I start simulations and doing the actual design, circuitry design, and then turn in complete fab files for you with the schematics, bill of material, Gerber files, BCBs. And I operate very inexpensive. So for those of you that may have such a need, please don't hesitate to reach out to me at this email or at the phone number that is provided right here. Okay, so today what I'm going to do, my friends, ladies and gentlemen, is actually I'm going to talk about LNB, SATCOM, K LNBs, low noise block down converters. These are the devices that you see out in the outdoor, right next to the antenna feed for the SATCOM terminals. The same thing is applicable really for 5G in the 28 millimeter bands as well, although it's a little bit different, but same principles can apply there too. So the system that I'm going to describe in this series and develop is available for OEMs. If you see that you can market this product, please reach out to me. I would work with you. I would provide you, just like I did for some other clients. I would provide you with the fab files, bill of material, everything. And then all you have to do is just build and market and sell this product. And then we would work out a deal where basically I get some royalties off that. So just to talk LNBs, ladies and gentlemen, they're basically this piece here that you see on receive only terminals for SATCOM, TV SATCOM, KA band. Also, if so, they're like this type here, and these are usually they're very cheap. I mean, I can buy them locally here in Jordan for $5, made in China. And the reason they're so cheap is because the the horn, the OMT, the waveguide to PCB transition are all casted, aluminum casted, and then or steel. And then the electronics itself is actually very highly integrated with an integrated block down converter that includes a local oscillator on it, a single chip, so which makes it very cheap. Plus, the performance of this is moderate. Now, contrary to that, you can look at systems that are fully transmit and receive, and these are used in government chains, government offices. They're used in to link banks together for merchandises, gas stations, worldwide networks of stores. And these usually you can see them like this, where you can see there's a power amplifier here, which is the buck, the block up converter. So this transmits as well as receives. And the LNB is right here, this piece right here. You can see that the LNB right here is coming off the OMT in here. And this piece in here, usually they're a little bit more expensive. They can be anywhere from a few $100s to thousands of dollars. They could reach up to $3,000 depending on the quality of those. So, okay, and now if you look out in the market, there's plenty of manufacturers of KALMBs. Basically, namely, just to name the ones that I was able to grab, Norsat, Canadian, I guess United States Canadian, Swedish Microwave here, European, and then XMW, which is Korean. Now, these are very high top level LNBs, along with hundreds of manufacturers of these cheap, low quality LNBs that are integrated with the feed horn. Okay, these are used for receive only, where these here are received with gateways that are much more expensive. Just to remind you, the band of interest that we are looking at, the KA band, really is divided into two sections. One is for military use and one is for civilian. Now, the receive frequencies, which we're interested in, that's where the low noise block down converter operates at. For civilian purposes, it's from 17 gigahertz to 20 gigahertz. Okay. So that's what I'm going to be designing basically, is a system that covers this one and this one as well. The military band is at the upper edge from 20.2 to 21.2. As you can see there now, the bands are really divided into sub bands. Usually they're about a gigahertz wide, and then so we will see how these LNBs a lot of times they're either band specific or switched bands where you operate at one band only and then you can switch to the other band using external trigger signal that it comes in from a DC level or a DISEC 22 kilohertz switching. Of course, for the K band, just to lay this out, the transmit frequencies are way up. As you can see, the distance between them is very high, so that you can get. And the purpose of this is to get enough isolation between transmit and receive. Okay, because the transmit they share the OMT, and you want the leakage in here to be so low that it will be much lower than the actual SATCOM signal. So what's the low noise block down converter? Well, they're really architected three types that I uniquely identify. First of all of the LNBs that are out there are really a single band conversion, meaning they convert from Ka band down to L band. L band is the frequencies that you see designated in here, which is 950 to 1950, sometimes 950 to 2450, it depends. But this is usually the L band frequencies where most modems are operating at. So this LNB is outdoor. It brings down from 17 gigahertz to 22, brings it down to 950 to 1950, and preserves the signal quality, the signal to noise ratio. And then this is fed into the modem that operates with these frequencies. Okay. Now, like I said before, usually this LNB is basically made of front end, very low noise, amplifier in here, which are operating at this frequency band, and they usually have a 35 to 30 to 35 dB of gain to bring the signal up from the dish. The dish itself has about a 30 dB, anywhere from 20 to 30 dB gain. Okay, 35 sometimes. For gateways, of course, you have much more gain. It could be 70 dBs. But in any case, for these smaller size dishes, we first of all amplify the signal at the Ka band with a 35 dB of gain, and then reject the image. And this is very important. This is an image rejection filter that we have to utilize so that we can reject not only the image if there is image interference, but also we would this one is to reduce the noise floor at the image, because that noise floor is actually translated to this IF frequencies as well as the desired signal itself, which is in this band here. Now, the way we do this, of course, is we use a mixer to mix the incoming signal at these frequencies with a locally generated carrier. That's local oscillator in here using a phase lock loop. And then we amplify and filter for harmonics, and then we cross beat them together in a nonlinear device in here, the mixer. And of course, there comes out of that is, the sine A times sine B is the sum and differences of those angles. So we get the up conversion and the down conversion of these two frequencies in here. And what we're interested in is the lower sideband, okay? And that's what we filter so we can get the lower sideband. And this will be the IF intermediate frequency section, in which the signal is also amplified by 35 dB. Now, of course, the local oscillator in here, it has to be accurate on frequency for the channel. And the way we do that is we bring in a reference, external reference at 10 megahertz through the IF port in here. We bring in DC and 10 megahertz. The DC in here is brought in here usually anywhere from 12 to 25 volts, in which we would, of course, regulate all the various voltages that we need. We need negative voltages for the HEMT gas fit devices in the front. We need plus 3 volts. We need 5 volts sometimes. All the various voltages that we need in here. And of course, the 10 megahertz, we leak it in here, recover it, amplify it, clean it, and then, of course, feed the local oscillator with it. Some LNBs have internal 10 megahertz reference, okay? This 10 megahertz cannot really cannot get the same characteristics as the one that is brought from the outside, because the outside one could be coming from a GPS disciplined reference. Plus, this could be coming from the modem. So this is common to the modem. And here, if we use a locally generated 10 megahertz, then we would have a phase shift on the this IF that we need to remove because of the fact that this is randomly phase starting in comparison to the modem 10 megahertz as well. So the best thing is to use a common 10 megahertz for the modem and for the LNB. So as a designer, what I would do is I would get the bands from 17.2 all the way to 22.2, which is both civilian and military, chop them into a gigahertz bands, okay? And then, of course, if I want this intermediate frequency here, I would have to subtract them from an LO signal, which could be anywhere from 16.25 to 20.25 to get these bands in here, the IF band. Okay? Now, we will see that this is, I call this type 1 because the LO in here is, the phase lock loop is really running at the LO frequency, which is here. And that's why I designated this TXLO, twice the LO. It's not really twice the LO, it's the same LO, but just to distinguish it from another case, we would use a Doppler in here to actually, or a quadrupler multiplier, just to multiply by 4, multiply by 2, this local oscillator signal so that we can have a phase lock loop that is operating at a lower frequency. If we needed these LO frequencies in here, if we can much simplify the phase lock loop much more if they were half of these values, 8 to 10, okay, instead of 16 to 20, or 1/4 of that actually. And in that case, we have either 4 times or 2 times the frequency multiplier, and here we can utilize that in here. Okay, well, and I'll show you. So this is type 1, is where you don't have any, the LO is really at an offset frequency, at the same frequency as the incoming signal here, however offsetted by this much here, of course, on the low side. So this injection in here of the low can be low side or high side. So in this case, I'm injecting really a low side for those of you that may be familiar with those terms. The overall gain of LNB is usually you've got the suction in here 35, so that's 70. And you've got about 10 dB of loss in the mixer, which is passive. And the filters. So you end up with anywhere from 55 to 60 dB. And that's what's typically what you find out in the market. Now, the second type, and I borrowed this from online publications, is we can actually bring in this signal, and then the LO would be running at, say, the same at this frequency in here, the same frequencies that we would get, except the mixer itself is actually pumped to a second harmonic. So this here is really half of the LO frequencies. Instead of being 16 gigahertz to 20 gigahertz, I'm using 9 to 8 gigahertz in here. And what happens is it comes into the mixer, and we don't multiply this like we would in the next session, next type number 3, where we take the LO signal and then multiply it by 2 to get to twice that, and then feed it into the down conversion. This one here, we use the mixer type in here. It's called subharmonically pumped. And that's a mixer type, and these are available from Analog Devices and Corvo and mini circuits. These are mixers that what happens is you come in at half of the LO frequency, and then what happens is the mixing process is emphasized at twice at the second harmonic of the LO. So what you do in that case, you end up using a lower frequency phase lock loop. Okay? And that's basically what you see in here. It says LO over 2. So meaning you feed these, even though they're at these frequencies, you still get a signal that is as if you were using twice that. Okay? And this is type 2. Now, type 3 that I showed in here, it takes the LO and really multiply it either 2 times or 4 times. Okay? And what I'm showing you in here, this is also a little different than these ones in here, these down conversions in here. This one in here is what we call an image rejection mixer or a single sideband generator. And what happens is, in this case, as you know, this filter in here has to reject the image, so that and a lot of times we need the image to be rejected at least 40 dB down below this carrier here, below the desired signal. And one way to do this is we would use to alleviate the strict filter in here, is we use a single sideband where we do the cancellation of the image signal via a hybrid, Quadrature hybrid, like we show in here. So you bring in the signal that you want to, in this case, even though this is labeled as 20 to 28, but it could be from 17 to 21 in here. We bring it in here. We have 2 mixers, and then the LO gets split. We multiply it by 2, so we get a higher frequency. And then we split into Quadrature LO, and we beat them, and then we have a Quadrature combiner, which ends up canceling out the image, actually. So this is an image rejection low noise block down converter. Now, the implementation of the circuitry can be Nowadays, we've been utilizing BCBs, just regular BCB with, as you can see, this is just an example showing you. Here's the waveguide aperture, the waveguide to strip line. Here's a probe, and there is a chain of LNAs, as you can see them. Here's a transistor in here, a second transistor in here. Then there's an edge coupled filter in here, and then we amplify in here, and then we go further. Of course, there's two here, one waveguide here, one waveguide here, two feeds. This is a dual fed LNB. So, or now this is traditional BCBs. We can use Duroid, we can use RO 4003 or 3003 from Rogers, or other manufacturers of PCBs, or we can do with low temperature covered ceramics, LTCCs. And these are much more expensive, of course. We can't really use this technology for consumer type. This is what we use for consumer and military type like these. This is usually restricted for aerospace and satellite modules. Okay, so what I'm going to do is I'm going to design my low noise block converter just like this one here, using traditional methods. Now, of course, the biggest specification for the low noise block down converters is their noise figure, that's the biggest figure of merit for them. Okay, and sometimes you see them specified in noise figure, but they can also be specified with noise temperature. And this here, I put this as a reminder for you that the noise figure and noise temperature are related by this equation here. As you can see, just so that you don't have to have a hard time remembering this formula. What happens is if your noise temperature is higher than the room temperature, which is 290, you start getting amplified noise figure, okay? Meaning, so that right now, if this was zero, if this was temperature zero, meaning it's freezing, the noise temperature is at zero, then the noise figure would be zero actually, which means your front end circuits, the LNB did not contribute at all any noise to the noise floor of you, that is of the incoming signal, which is only achievable is with the cooled liquid nitrogen or something else. But as soon as you, for instance, if your noise temperature is room temperature, you get this one. This one becomes 1. That's 2. So log of 2 is 3 dB. 10 times that is 3 dB. So noise figure 3 dB. That's really is noise temperature of room temperature. Okay. All right. So let's. So how do we design this? When we're designing a low noise block, frequency translation or dot converter, the first thing we would want to do is lay out the frequency plan. And the frequency plan is as follows. We know that our lowest and highest frequency for every one of those bands, like I said before, we chop them into 1 gigahertz bands. And then you basically, what you want to do is you derive the LO frequencies that are required so that your IF frequency is between 0.95 and 1.95 gigahertz, or 950 to 1950 megahertz. Of course, the IF bandwidth is the same as the RF bandwidth, which is a gigahertz in this case. And at the same time, you need to figure out where is the image is sitting at, because these are the things that you need to lay out so that you figure out, so that you can specify what is the image rejection of your system, and then distribute that to be implemented in your front end primarily, which means that you can come up with the specifications for the front end band pass filter or the image rejection filter. And this is calculated right here, you can see. So for instance, if you try and receive 17.2 to 18.2 with either an LO that is at 16.25 or 8.125, and that's meaning, or even at 1/2 of that, which is 4.7 something. So in that case, the image sits at these frequencies from 14 to 15 gigahertz. So your bandpass filter at these frequencies in here has to be lower than 40 dB, lower than minus 40 dB if your bandpass is at 0 dB. But of course, this one is somewhere you might be able to build these filters, we'll say insertion loss of 3 dB. In this case, this would have to be at minus 46 dB down. Okay, so this is very simple and very straightforward. Let's review a typical LNB for the Ka band. The first thing we would specify, of course, is the noise figure. Usually, typically, these LNBs for Ka band, they're somewhere between 1.5 to 2 dB, okay? And then the LO stability, of course, is how stable the local oscillator signal, because the SATCOM signal doesn't drift at all. Okay, the satellite itself is geostationary, so you don't have any Doppler on it, but your local your incoming signal from the satellite has a very high precision frequency reference, so there is no shift in frequency. So the only shift you encounter in that case is an offset from the actual local oscillator signal that you would need. And that, of course, has to do with the reference stability, that's the reference that we feed in here. See this 10 megahertz in here? This 10 megahertz determines how off you are from these actual frequencies that you need to land your IF at these frequencies. In a lot of cases, your modem is able to pull in this frequency. It knows where that frequency should be because there are pilot signals and pilot symbols in the incoming signal that from it, the modem can figure out how your offset frequency, and it would correct for that. But in a lot of cases, a lot of people prefer not to put that issue on the modem and just fix it in here so that you use a very stabilized 10 megahertz in this case. Okay, so then the LO stability of the low noise block is really dependent on the external reference in this case. The phase noise is really, in the next sessions, we will see how we derive the overall phase noise for the low noise block. But it's an accumulation and contribution from several sources, and mainly from the phase lock loop and the reference itself. But these are typically the offsets that you would need, okay? So at 100 kilohertz offsets from the center of the carrier, you would need the phase noise to be at minus 90 dB below the carrier per hertz, of course, that is, okay? And so on. So in a lot of cases, these are becoming very strict for high level QAM modulations. So before you design the LNB, you would have to system design this. You start out from a reference giving to you reference phase noise that you have, and then you compute the worst case phase noise can become from the LNB itself, okay, from the phase lock loop, plus from the LO amplifiers and IF amplifiers as well. Of course, the input VSWR specified, output VSWR. The input VSWR, of course, that's an input waveguide. So waveguides have very good return loss. So you usually end up having much easier time to do this, where the output sometimes is a little bit more difficult because although I will show you how when we design the IF section, how to optimize the return loss, where you can use actually bypass to increase the return loss on this case. The convergent gain, like I mentioned before, it's always somewhere from 50 to 60 dB. Typically, that's what you would get. Because that number here, in conjunction with the dish or the antenna gain, which is about somewhere from 25 to 35 dB, that puts you with the SATCOM signal being somewhere from minus 100 dBm to minus 120 dBm. That puts you somewhere within the range of the L-band modem capture rate, which can give you a sufficient signal-to-noise ratio. Gain flatness is usually specified over the entire band or over specific sections of a band, okay? The the 1 dB outer compression point usually is plus 5 dBm, sometimes plus 10 dBm. And then, of course, the third order resistance point is always 10 dB above that, which is at 15 dBm. Now, the output P1 dB, you really need this to be, yes, moderate enough so that you don't have any nonlinearities and clipping in the IF signal, but also you don't want it to be high because higher value in here means that your IF stage can actually have high power into the modem. And the modem is a very expensive piece. And of course, wouldn't want to damage the modem with if say, for instance, if the IF stage oscillated where you can get full, if it was, say this, if it was plus 15 dBm, that would be dangerous, of course. So this value always has to be carefully treated so that you don't damage the modem, okay? The reference external reference signal is always 10 megahertz. Sometimes some LNBs, they're starting to come out with the frequencies, reference frequencies at 100 or 200 megahertz. And I will talk about that in the next sessions because a lot of times this reference frequency you need to divide further to get your reference frequency for the phase lock loop. And the lower the division of this is the better phase noise that you can have, close in especially. So that's why some people right now are starting to move up to 200 or 300 megahertz. Okay. The RF input level, of course, you don't want to go beyond this, and you can't really go beyond that because this is satellite signal, and this dish is pointed at the satellite. There's no interference that could come in and radiate into jam your antenna into a signal that will result higher with a signal higher than this, because these LNBs in here, these LNBs that we will detail in the next sessions. And even in this session today, we'll go through some. These are very sensitive, so they can get damaged easily with high input power. Okay, so the spurious levels requirements at the IF frequencies that goes into the modem, they're really related, either signal related, say the second harmonic of the incoming signal, or power supply related. Let's say that you have switching frequency regulators, high efficiencies, switch regulators. Those would have spurs, or harmonics. Okay, harmonics meaning harmonics of the LO, harmonics of the LO beating with the incoming frequency, or harmonics of the incoming signal. Well, these are the type of numbers that we would want. Okay, basically you put your LNB. When we test this, we make the LNB, we put into the LNB front end signal that will give us an IF signal level that is at minus 10 dBm. And then we measure all of these, and they have to comply with these. They're always like minus 50 dB to 60 dB below. Now, the LO leakage on the input side, which is the waveguide side, has to be less than minus 50 dBm. And that's very important because you wouldn't want your SATCOM dish to radiate the LO back to the satellite. Okay? So you would want that signal really low. And a lot of times this is easy to achieve. Just because the frequency of the LO is much lower than the incoming frequency, and therefore a lot of times the waveguide itself that feeds the horn, its cutoff frequency is well above the LO frequency. The image rejection is always universally almost 40 dB down, and that's what we talked about. Okay. Now, the other stuff in here, of course, the input waveguide for Ka bands usually is WR42 or some other variants of this. The output connector, okay, that's for the IF on this side. Okay, this one usually is either N-type or F-type. F-type is this is those 75 ohm um, cables that usually feeds a lot of modems are 75 ohms. I don't know if you can get 50 ohm F connector, but or N-type. Okay, N-type, which is rigid, big, and but mechanically very stable. All right, so the WR242, which is the input waveguide to the LNBs, these LNBs, that's a standard. Its recommended frequency range is between 18 to 26, okay? Although we are receiving really 17.2, so, but this somehow they typed it that. Its cutoff frequency, if you calculate the cutoff frequency for this waveguide with these dimensions in here, which is 10.67 millimeter by 4.32 millimeter, the cutoff frequency is 14 gigahertz, okay? Now, this is for the lowest mode, the TE10, but for the second mode, the cutoff frequency is 28 gigahertz, okay? So keep that in mind. The both phase noise and the gain and noise figure of the LNB is really measured using almost a single device from Keysight. Also, these are available from Rohde and Schwartz. But this is just an example that I grabbed from one of the SATCOM manufacturers. They were displaying this as an example of a customer unit. So basically, here's your gain. This is using the N8973 agent analyzer, signal analyzer. You can see that the gain in here is between 820 to 2100 megahertz. You can see that the gain is right now is at these values in here, 58, 58, 57. Okay, and then the noise figure is this curve here, which shows that it's 1.4, 1.4, 1.3, 1.4. That's typically what you get. Okay, the noise figure also this here, these adjuvant analyzers, even this model, they have a function for phase noise. So you could use this one, although this one here, they use another one here. Phase noise is adjuvant E82570. Oh no, that's a signal source. That's the signal source used to test the phase noise. And that's very important because you would want the injected signal on the front end when you're testing LNBs. You would want that really to have at least 10 dB better phase noise than the LNB itself. Otherwise, this is really, and I fell into this before in while designing X and KU and KA LNBs. Is sometimes you test your phase noise unknowingly with a signal source that itself doesn't have a good phase noise below the parameter the levels that you want to test it at, and you end up thinking, well, my LNB fails when really it's not failing. It's your signal source is not clean as enough to go down to so that you can see it smothers the phase noise measurements, and you don't see that anymore. All right, and there are, of course, now this is not the only one way to test this. There are much more advanced new equipments that you can utilize. So now let's look at, okay, here I am, and I would like to design an LNB using one of these systems, either like this. So what I want to do, I want to start searching for components, off-the-shelf components. Okay, preferably if I can get mimics where I can just glue them together and then rapidly prototype and get my product out. So here I am. I'm going to try to search what's the current status of the LNBs. Now, the other thing I forgot to tell you is that we need to sometimes in some systems, because this here, this LNB here, in a lot of cases, the most critical portion fulfill the noise figure requirements or the noise factor or the noise temperature requirements is the noise figure of this is the design of this low noise amplifier in the front end. Okay. So some people, what they do is they say, okay, I want to get an external provider that will provide me with an LNA that has a waveguide on the input, but has say a K connector on the output. That way I can get this here, remove that critical side of this design so that I can design the rest of my system, but utilize this. And this is a case where a bunch of companies make LNAs like this, Erzia, which is in Spain, Europe, or Amplitech, okay, whom I worked for before, have actually a waveguide to K connector LNA, okay? And so in that case, all you need to do is get that, and of course, get your signal amplified. So now, beyond that, your LNB noise figure is irrelevant in this case, because this one here has about 40 dB of gain. So, and as you know from the noise figure equation, that first component that you hit, which is this component in here, your noise figure is really going to be based on that, because if this has, say, a gain that is at least 20 dB, then it's irrelevant what the noise figure of this section here. It's going to contribute at most fractions of a tenth of a dB. So in the overall, it doesn't really add up anything. So a lot of companies, what they do is they buy one of these connectorized, put it in, and then get their signal, and then start splitting the signals and go into a bank of these noise block down converters and get their signals out. And in this case, basically, you're constructing a Ka band base station in this case, or a complete spectrum reception from 17 all the way to 22. Or you can do it just for a single one. And I worked on a project like that, where basically we use this from a manufacturer and then a single, so it's the same one. Sure. So it's the same here, except this piece is provided by somebody. Okay, let's move further. So the first thing I want to look at is the front-end filter. So the front-end filter in the block diagram in here, this front filter, remember the function of this is to reject the image and to reject interferences, but mainly to reject the image. So, and this is a critical filter because it's a printed filter and it operates at this frequency here. There are some companies that are starting to produce these filters and sell them, mini circuits, nulls, but a lot of times just the headache you get from trying to get them on the board to perform as good as what the specified part is becoming a big headache, so that you would rather just basically design your own. This is a filter that I did for a client. Okay, this is one time when I captured it. It's not really optimized, but you can see it's most of these filters usually it's this topology in here, the edge coupled filter. Okay, so you end up this is here is analyzed in HFSS along with the first device that hits this filter goes into. So just the analysis of this, you can get the spectrum response like this. So the main important thing is you come in here where the upper frequency of your image and make sure that at this frequency you're really getting good rejection. In this case, you have minus 41 dBs, and that's the rejection of the image. Now, this image, you get more reduction forward a little bit contribution, because a lot of times the amplification is focused on this here, on this band here, rather than on this. Okay, so you get little help. Now, this is an example of an LNB section that I found on the net. Somebody was tearing down a SATCOM terminal, Basically, as you can see here, this is Ka, I think, not Ku, but this filter in here was a Ku band next to it. This was a dual Ka, Ku, but this is the Ka section, I think. So here's um, the OMD aperture with the two probes for the vertical and horizontal. And so these are actually the LNA devices that we're going to look at shortly. But this is the image rejection filter, as you can see in here. As you can see here, there's a T-junction splitter, and we go into these two simultaneous filters, okay? And the reason for doing this is because this filter is a little different than this. So you end up in the front end, common amplification for two bands, and then you split them so that you can have different image rejection at each one of these, and you don't convert separately. Now, let's start looking at, so what about the other components, like the mixer and let's look at the mixer in here. We need to look at the phase lock loop. Is it external or is it built into the mixer? The IF stages, we're going to look at all of those. So let's look at what's out there commercially available currently, today, in this October month of 2024, because as you know, now a few years later or tens of years, if somebody watches this, they'll be seeing this technology and they would have exceeded this capabilities of these devices that I'm going to show right now. But today, as of October 2024, I'm going to go through some of these devices that are available to utilize in this LNB design. Let's look at first the mixers, okay? This is from Analog Devices, and what this is, you can see there is a quad mixer in here, and quad inputs and quad LNAs. Of course, the noise figure of this LNA, they call it LNA, is not really acceptable for us as an LNB. It's 9 dB in here, but of course this is internal. This is really an amplifier. It's not an LNA. The LNA is, if I were to use this chip in here, it would be external right here. But this is a highly integrated receiver here where you can see that the mixing, and there is an IF, and then differentially you get these signals out. And of course, the LO can be fed at 1/4 of the frequencies you can see in here. Look at this, which is really nice. So instead of using an LO at 16 gigahertz, you use basically 4 gigahertz in here, and you can get 16 gigahertz to beat down with the 17 to 22 and produce these. And this can be used actually for 4 bands. You know, this is highly integrated. It's got some other features in there where it gets programmed, of course, over SPI control, bus, and there are ways to monitor the temperature and so many other stuff as well in this one. So this is about right now, sells about $90. That's the posted price for this. And of course, that's expensive. As you can see now, LNBs for TV, K-band TVs, they're still about $5. So you wouldn't want to use a device like this in an LNB, of course, commercial LNB. This would be for one of the high-end ones. Here's another higher. Now, this one here, of course, the LO is external coming out, so you would need a phase lock loop externally, okay, and this device in here. Well, they did that for you. So they said, okay, well, you can come in K-band, you bring in internally, we would have a local phase lock loop. Here's the phase lock loop. Okay, so basically you get the reference is fit to this. And then the tune voltage, there's a loop filter in here, which you build discretely outside. And this is basically the tune signal that goes into the VCOs. Sorry, this is the error signal in here. And of course, this is the reference, the crystal reference is fed right here differentially. So you feed in your 10 megahertz here, gets divided, gets frequency compared with the local oscillator, local voltage controlled oscillator, and you get an error signal, this error signal then goes out and gets integrated and filtered and fed back to correct the VCOs. Okay, and this device in here is sells about $54, which is very reasonable, considering that this here includes the frequency local oscillator. Okay, of course, the noise figure of this is 7, so you would need an external, still an external low noise amplifier, and you need the image rejection filter. Your IF suction, the overall gain is about 36 dB, so you still need an IF suction in here to amplify the signal further. Here's another device, which is this, and then this device in here, they lifted out for you so that they didn't combine them. You see here, you get the quadrature signal or differential signal. They combine them and give you a single-ended IF out, where in this case here, they give you separate I and Q so that you can build your own. It's more flexible with this chip. If you need to do more separate quadrature signal processing with this, okay? And this can be also used as a direct converger receiver as well, but it can be used as an LNB because it's 17 to 22. And of course, you got switchable amplifier in here, so you can come in from 2 different sources. Here's another one also. And this one in here, you feed in the LO, it gets multiplied by 2, it goes into quadrature hybrid that splits the LO in phase and out, 90-degree out phase. And of course, you bring in your RF input signal level here, and then it gets mixed, and you get an IF signal in here. So this would be utilized for an image rejection type low noise block down converter. Noise figure, like I said, is not good enough to be without an external LNA. Gain is moderate, 14 dB. This one sells $30, which is much cheaper, as you can see, because it's lower ohms. Now, here's one from Curvo. You know, the ones prior I described here, they're all from analog devices. This one's from Curvo, and it's very much the same as this one here. So they really compete. So they give you the same thing. All right, so we go further. Here's one from this one is the package is a little bit different. It's much more suited more toward highly integrated like ceramic type mounting, because it's got this is wafer level chip scale package with the solder balls, okay? And of course, the hybrid that combines the quadrature signal is always externally. On all of these, you have to utilize them externally, okay? So in this case, this is right here. Okay, this is from Sumitomo. It's Japanese. This is what used to be Fujitsu, this part. Okay, front end mimic low noise amplifier. So now we're gonna go and look. So what we covered basically, if you go back to this block diagram in here, we covered this mechanism in here along with these ones in here. So this portion. What we need to do now is look at this. What's available for this? Now, what I will show you next is that if you try to get this as a mimic chip, it's very hard to get a mimic chip that has the noise figure that will give you an overall noise figure of 1.5 dB for the entire system. And that's why you almost have to get discrete implementation from the transistor level, because you need to optimize the amplifier for the noise figure. And I'll show you that in a minute. So let's go see what's out there. And so if you review the devices out there that are available, you can see stuff like this. You know, you can get 25 dB at this band, but noise figure is 1.3. Now, of course, 1.3, add to that the 0.2 dB from the waveguide to microstrip line transition, you're up in the 1.5. Add another 0.2 dB also from the rest of the system, and you end up 1.8, 1.6 at most. So This is if you like to try this. This is, but it's already at 1.3, and we're looking at 1.5 at most. Okay. Now the same device you can get it from some other variants. These are curve devices. MACOM also has no low noise amplifiers like this, 1.4 dB of noise figure. Okay. Now, although these are what happens is what we will see in the next sessions, you could start out with discrete transistor implemented LNA, single stage, and then use these as a second stage and third stage. Because remember, the front end, you need at least 30 dB of gain. So you need at least three devices, or actually two devices. But one of them has to, if you can't use these mimic devices, they're commercially available, you would need to implement your own transistor level. Mini Circuits as well has on this game. This is one of their devices. Same thing, 1.5 dB of noise figure. And then from there on, you start getting devices that are in the 2 dB noise figure. These are good for like second and third stages so that the overall noise figure doesn't contribute as much. And you can still get devices with high gain, like this one's 25. So this one here would be good with a device with another LNA that precedes it with, say, a gain of 10 dB. So this would be perfect. Same thing in these devices. And these devices are not cheap. They're, let's see if I put prices on here. I didn't put prices on these. Oh, this one's $50, but they're always 50 some dollars. Okay, here's one for $70. Okay, let's see, they're 2.5 dB of gain. All right, so as you can see, these devices that we just reviewed, the noise figure is a little high. So for a KA LNB SATCOM, we need really an LNA that would have a noise figure of, say, between 0.8 to 1 dB. That way, when we add the loss due to the waveguide to microstrip line transition and the another 0.2 dB from the rest of the circuit, then the overall noise figure is still below 1.5 dB or near 1.5 dB. Well, that's what happens is we're going to turn into these hemp devices that are commercially available. These devices are from CEL, which is California Eastern Laboratory, what used to be at one time, or NEC at another time. These devices have changed, like 4 or 5 different manufacturers produce these devices, and they're available for KU band and for KA band and for GPS as well. Okay, you can buy them, and they have very superior noise figure. As you can see, we will see in a minute. Let's see, noise figure in here. You can look at this noise figure, 0.3 dB. That's of course, that's F min. That's what this device has. If you were to de-embed the trace at the output, 0.3. The Ka band ones, you can see this one here, CE3521, 0.7 dB, and CE3520 is 0.55 dB. Okay. So and these are the very low current. You're talking 10 milliamps. See, the drain current in here is 10 milliamps, and the gate voltage is negative 0.2 volts in a lot of cases. And the gain is, of course, is moderate. Their gains are about 13, 12 dB. You can get 12 dB easily with these. I have designed KU band amplifiers with these devices, and they work really nice. These are available, and their prices in like the hundreds of units. They're like $1. Okay, so all of the LNBs that you see out there that are trying to reduce the cost, they're really based on these devices in here. Okay, so in this case, for KA band, you could start out with this device here with the 3520 as a first stage, and then you can follow it with this stage here if you want. Okay, so or you can just do 3 devices sequentially and get your 30 dB of gain, yet your overall noise figure will be barely 0.6 dB. Okay. These devices are also nowadays sold through CDK.co, Japanese company that produces them. I don't know. It looks like the technology right to these devices is out of date. So now they're being produced by a lot of companies. Oh, Renaissance, by the way, also manufactures them. They're produced by many of these companies. Okay, so this is from NEC application that I saw. So this is a KE band suggested chain, which is like I said, 3520 first, and then two devices with these. And then you, of course, the reason for this is because this one has much lower noise figure, where this one here has zero point 0.7. Of course, this is a single transistor. So now, uh, as I will show you in the next sessions and the next videos, I'm going to design these from discrete, meaning you get the data sheet, the small signal model as parameters and noise parameters, and then you have to match them. You have to create the input match and the output matching circuits and optimize them for noise figure. Okay, so these are not easily um, uh, built because they're marginal stable. So you end up first having to stabilize them. And then once you stabilize them with like resistors on the output, and of course, you still need to gate and drain, provide them with voltages. You need a bias network. So you need to create the S parameters after you added the bias networks for the drain and gate. And then you need to, and the stabilizing resistors. And then again, get the S parameters and again, draw the noise figure circles, noise factor circles, and gain circles, and find out where the optimal point for your operating frequency, and you can derive from there. And it's a pretty interesting process. Okay, so I'll show you how to do that in the next videos, of course, because we can't really rely on using these mimic chips that are commercially available nowadays. The noise figure is just too high. We can't utilize them. Okay. All right. So if you look at the closer at these devices, okay, they give you the noise figure as a function of frequency at the 10 milliamp drain current, and drain voltage is 2 volts. So the noise figure for this one, 20, is anywhere from 0.5 to zero point 0.8 dB. Okay, so that's the range, and that's what you see here. Okay. And they can operate anywhere from, say, 18 to 24 gigahertz. Okay. The same thing for the 3520, you can see here. And by the way, you can see that when you look at the noise figure for this device in here, it turns out as a function of the bias voltage, the drain current, it has a bowl shape. So that's why you look at this and they figure, well, we need to bias the drain at 10 milliamps. And that's why all of their measurements in here are basically based on 10 milliamps. And that's what we as designers utilize as well. We exactly use these parameters because they found that's the sweet spot for the noise figure, the minimum noise figure. That's the other one, 21. And you can see it's from Renaissance now, this one. Okay. Now this package in here, of course, is a different package. Okay, that's the 21 device, and that's why this device here has higher noise figure. Okay. Okay. Same thing in here as a function of the drain current, you get the ball shape. So at 10 milliamps, again, you have an optimal value. And of course, that would be the gain at 12 dB. Okay, so like I said, there's a closer look at the chain. As you can see in here, this guy that was tearing down this, he did the measurements too, and you can see the drain voltages were at 1.4, the gate voltage minus 0.35. These are similar devices, they're not the same, but you can see that the chain in here, you go out from the probe, which is this is the transition from circle waveguide aperture into microstrip line, and you end up with an input bias circuit, an input matching circuit, and an output matching circuit, okay, in here. And you have the gate bias network and the drain bias network. This is what you see, these passive components in here. And you can see this one is probably the same device because it's minus 0.4. Okay, so you end up with a chain that's like this, and you go into the now I checked on the internet the prices of these devices. You can see at 10,000 units, they're really cheap, 70 cents, 70 US cents. All right, the IF stages. So we're going to go into the next uh, the next part of the system, which is, should have put that slide, repeated that slide, which is this stage here. So we did look at this here. We looked at this. We looked at this. Now we're going to look what's out here. We need a filter first that would filter out this signal, the intermediate frequency signal, between 950 to 1950. These filters, turns out, most of them are ceramics, and they're available from a lot of people. We can have LC filters as well, and they're available too. But ceramics are such wonderful devices and very cheap. And the amplifier, there's plenty of amplifiers for this L band in here. And of course, the noise figure in here is irrelevant because once we pass this point here, really the contribution of this is meaningless to noise figure. So let's look at what's out there in the commercial world for the IF stage, the intermediate frequency stage of the low noise block down converter. Well, the first thing is you look at these. This is bandpass filters. These are from many circuits. You can see there's plenty of devices to go between 950 to 1950. So there's plenty, and they're tiny. Okay, here's another one's set of ones. You can see these. Now, the only thing you have to watch out is that these have such a nice frequency response close to the passband, but beyond that, they flare out. So if you have signals that leak out in the IF, you might think that gets rejected, but they really don't get rejected. You might want to make sure that you need a combined effect of these filters. These filters can be used, and then you use another low pass to knock out all of these ones. Here's some nice filters in here, and I did this on system view, so in preparation for the coming video. This is how they look like, some of these devices, as you can see in here, 950 to 2200. It's really tiny. Okay, here it is. It's like 2 by 1 millimeter. It's an 0805 package. Can you imagine? It's as small as a capacitor. Okay, here's another device in here. This is a low pass filter. Like I said before, a lot of these devices, they come back and flare even worse. When you put them on the board, this gets much higher. At most, they could be out here. So that's why you need to always consider using some kind of low pass filter, same technology. Also, filters that are made the same frequency, 950 to 2150 for an IF, these are LC filters, so we could utilize these, but these are bigger, as you can see in here. Their size is much bigger than the ceramic, and they're much more expensive. These are out in the 40s and 50s. Some could be $20. Another one of these is an example. These both are from mini circuits, but they're available from other sources as well. IF amplifiers, there's plenty of these, mimic chips. So we just need to make sure that we pick one, and we're going to look at the system view chain budget link calculation in the next videos, and you're going to see how the effect of these. We can't, these can't be arbitrarily chosen. But this is 20 dB gain, and here's the rest of the stuff. You can use this one in here, another one. They're usually a few bucks for mimics. This one is much cheaper. This one is like $1. Okay, here's from Curvo. This is a nice one here as well. Okay, even though we're operating 950 to 1950, in a lot of times you don't want to pick a device that is very narrow. It's because it will have a horrible slope. So you need a device that goes up to like 6 gigahertz, and then that way you can get a real flat IF response. But that makes it risky because that amplifier is amplifying things that are beyond the 1950, and so you need to make sure that you really try to tune this so that the gain is not as good at those frequencies. So you need to be careful. Now, remember, if you implement an image rejection low noise block down converter, you need a quadrature hybrid, surface mount quadrature hybrid. Let's go back to this block diagram. Not this. Okay. Well, this one here. Okay, so if this device or any of these devices, you do need a quadrature. Here's IF1 and IF2, so you need to take these are quadrature, use a hybrid 90-degree to reject the image. And this can only be done with a hybrid, okay? Like this one here, see, they used it here, they showed it. So here's the IF out. They brought in the from the two mixers in here. So this one in here, remember that even though this is an image rejection mixer, but really the image rejection capability is really a function of the mismatches between these two branches. Okay, so the quadrature impairments of the INQ image rejection mixer really determines how good is the image rejection. And that image rejection, you don't want to end up with making it worse and utilize and realize that your image rejection down converter is really it's as bad as it can be, that you wouldn't want to, you didn't get any benefit from an image rejection because now the image is getting recreated by the quadrature errors of either the hybrid or the down conversion itself. And so here's a Zinger, of course, from you guys remember this, Merrimack or whatever their name is nowadays. We can use this hybrid in here, and this operates at the IF frequencies. Okay, here it is here. And I put this diagram, which shows as a function of gain error, quadrature gain mismatch, and phase mismatch, and then the image rejection, the achievable image rejection. And you can see if you want to be in the 40s, your gain error can't be, worse than 0.2 dB. And that goes for this one here. And your phase error cannot be at most is a degree. And yet, when you look at this, of course, it's plus minus 5 degrees, and the amplitude imbalance is about plus minus 0.5 dB. Okay, well, the amplitude is okay for this, but this plus minus 5 degree, you're out here. So you're in the 20s of image rejection. So that's just to show you the ahead of time how difficult this process is going to be. Now, so let's talk about the other. So we finished the down converter sections, except we still need one section, which is this one here. How do we get from waveguide into the LNA here? Well, to do that, we need to get from waveguide to LNA. We need to design a waveguide to printed circuit board transition. And that's the most critical part. That's the hardest, toughest job I had faced before. And to do that, I'm going to take you to my basically, I did a series of videos. I'll show you in a minute, and basically how to design the various types of this transition. So here's a square waveguide. You could use a coax to a waveguide. Of course, in our case, we have a board sits out here, so we really don't have a coaxial guide, coaxial line. We really have a pin that goes from the printed circuit board, which sits in here, down to this. And this one, my video is at this address here, and you can watch that, how to do this, okay? And I have a various types. Okay, here's one which is inline like this, rather than the other one, which is, as you can see, it's orthogonal. And here's another one, which is inline using a coax, like this, or steered taper. Here's another one, which is microstrip probe. All of these are showed at these addresses, and here's another one as well. Okay, so let me just take you to this is, if you can see, go to my channel, you will see these transition videos down here. So you can see here is the KU band. This was done at KU band for the coaxial. Here's another transition. Here's another transition as well. So you can go watch these if you like. So that's basically what we that last part is how we're going to do it. Okay. So really, again, just to go back to the top of this and go back to the block diagram. So how are we going to design this? The first thing is we would want to do is design the transition in here, get the S parameter equivalent of the output, which is one port, a two-port device, of course, one port, one side waveguide, the other side is one waveguide to printed circuit transition, okay, 50 ohm. And then once we get that, we store the S parameter for the transition from waveguide to microstrip line, 50 ohm. And then we take that and utilize it along with a low noise amplifier transistor to design the amplifier. Okay. So once we design this section in here, which is basically includes the LNA and the waveguide to printed circuit board transition, then we can go further. The next thing to do is to design this microstrip filter in here. Now chain this together and make sure it works, stabilize and everything. Okay. And once we do this, now it's much easier. Okay. This one in here, we can utilize one of the devices. You can build this discretely if you like. And some LNBs do that. They use Schottky dies to implement discrete mixer, but we don't want to do that. That's too risky. We're just going to get a mimic chip that encapsulates the phase lock loop and the everything in it and the mixer. So all we need to do is just feed it RF, get the IF out, and feed it with 10 megahertz reference, okay? And then, of course, the easiest job is the IF chain in here. We're going to design that. The DC to DC converter is basically, we need a way to generate the voltages that are needed here. We need a negative voltage for the hemp devices that are used for the low noise amplifier in here. So we need to generate negative voltage. We need like 0.2 dB, 0.4 dB of gate voltage on these. We need to have a protection so that these devices, you need to hit them with negative first before we hit the drain with a positive voltage. So there is a bias sequencer in here that will switch it, make sure that you don't apply the drain voltage on these until the negative voltage is there. And then on the shutdown, you do the opposite. You take out the drain first, and then you turn off the negative voltage. Otherwise, these devices will blow up. And of course, we have the S parameters and system model parameters for all of these stages. So we have this, we have these, we have the phase noise of these reference that we want to use. And then we have the phase noise specified in here, we can model it. So that's what we're going to do next, okay? Well, this is it, ladies and gentlemen. Now, if you happen to be in this business, the LNB that I'm going to attempt to design is a little bit different than the LNBs available out there, like these. I'm going to attempt to make it really smaller than these, really tiny, okay? Such that it could be placed almost on top of a standard waveguide to coax transition, which is almost 1/8 of this size. Okay, so if you happen to be in this business and you'd like to get this design, I will definitely share it with you, and we can both partner on this so you can sell this to the market. Well, this is Dr. Mohamed Nezami again. Please visit my channel and share it and subscribe, please, because that keeps I can keep going with these good videos for you. I hope whether you're a graduate student, design engineer, or researcher, I hope you benefit from this and be on the watch for the following videos on this because that's what I'm going to be doing. If you happen to be in need for any high frequency design offshore, if you're in the United States or Europe, let me know. You can reach out to me at this email. I'll be glad to help you. Okay, ladies and gentlemen, thank you so much and have a great day. We'll see you on the next video. Okay, we'll see you on the next video. Thank you.